Hello. Hey everyone. Thanks for having me. I'm Prabal. I'm one of the co-founders of Avail. At Avail, we are building a data availability focused blockchain and a unification layer on top. Today, I'm not going to talk too much about data availability and how that works. I'm assuming some understanding of it, but if not, happy to answer more questions in the end. Today, I'm mainly talking about a key piece of infrastructure which we have been building along with our partners, and that is called the vector bridge. It's a trust minimized bridge between any grandpa-enabled gadget to Ethereum or any other blockchain, right? So it's a verifiable computation layer of grandpa gadget. I will try to come to what that means, but one of the things that we have all realized in the Ethereum land is that the rollups are the agreed upon way to scale blockchains. That's the way that we are seeing that execution sharding did not work too much, and then there were multiple of these L2s getting to scale Ethereum base layer. And from 2023 till now, we have seen a huge demand of data availability on L1, and this is seen by the surge of L2s that we are seeing in production today. Now, what does it mean for a rollup to have data availability? Not going into the rollup construction and what it means to have the data available, you can think of the rollup having two major components. The one becoming a settlement layer that Ethereum is because it's an L2 on Ethereum. And then the second component is data availability, which is pushed onto the DA layer. This is where Avail comes into the picture. The Avail DA essentially helps your rollup scale in terms of data publication costs. And then there needs to be an attestation. This is the key component that I'm going to talk about today, that how this attestation works between Avail DA and Ethereum, but you can replace Ethereum with any blockchain or even a light client of your own. It can mean a single piece of code on your laptop being able to verify entirety of the consensus of Avail DA and any other chain which has grandpa as its finality gadget. So this is Vector X. It's a zero knowledge proof verified consensus verifying bridge for arbitrary messages, which we use for arbitrary messages, but also for Avail token bridging. But what does this mean? It means that it provides an attestation through a zero knowledge proof that some data was published in the DA layer to any other blockchain. And it scales beyond just the attestations, right? So it enables not only just the Avail token, but any arbitrary message. What that means is that if you have any message included in a blockchain, that blockchain might have a consensus layer. This consensus layer, let's say it's a babe and grandpa, so babe does the block production and then the grandpa finalizes it. You need to prove that the validators have agreed to include a message on that blockchain. That message can be anything. It can be a transaction in a particular block which has been finalized by the validators. That's how arbitrary it can get in terms of what it can prove. But essentially, that can be wrapped around to make it about a token bridging. It can be about an attestation bridge. It can be even more. It can be arbitrary token transfers. It can be NFT transfers. It can be about anything else, right? So this technology that we have been building is about arbitrary messages, but it can be wrapped to make sure it works for almost everything else. But before I go into that bit of detail, what about the other side? A bridge cannot be like only connecting one side, right? That is like a unidirectional bridge, which will be like, not that too useful. So for the Ethereum to Avail side, we have also created a bridge, which is again a zero knowledge proof verifier of the Ethereum consensus. So not only do we have a gadget to prove any substrate style blockchain, but also any Ethereum or Ethereum forks. That is done through Helios and Telepathy X. We right now have in production the Telepathy bridge developed by Succinct, but soon we are going to replace it with the Helios because that is being maintained right now on the consensus core level. What does that mean? That vector X and Helios together make up the zero knowledge proof based, so that's a validity proof of consensus on bidirectional level. Now, Avail consensus, as you guys must be very, very familiar with any other substrate style blockchain almost, is that it has a block production engine called Babe and then a finality gadget called Grandpa. These two together make up the consensus of Avail and similar blockchains. Now, Avail's finality gadget is pretty complex, right? And this is true for any Grandpa-based consensus. One of the superpowers of the finality gadget that was developed by the Polkadot community here is that it can attest to multiple blocks, and not only that, it can have a particular common prefix attested, which makes it very, very hard to verify inside a zero-knowledge proof. So if I take a little bit of a detour, right? If you think about how blocks get finalized, a very simple mental model is you have a block, you have a set of validators. The validators all agree or sign on a particular block header. That's how the block headers get finalized. That was too simple. What that meant is, if you took that route, you have to wait for immediate finality. So that's the Tendermint style consensus. Every block that is ever published is always finalized. Before finalization, the next block cannot happen. But that leads to a crucial problem of liveness, where if the validators are split, let's say that this is a split of validators, and this group doesn't agree with this group, then the next block cannot get produced at all. One thing that Babe and Grandpa together do fantastically is how the block production keeps on continuing even if there is forks in the chain. And different validators can vote on different forks. But this makes it enormously challenging to implement this inside a zero-knowledge proof circuit. So there are two key problems. One is that the gadget uses ED2551 signatures. This is incredibly hard to verify inside Ethereum or any smart contract. So even like, let's say you have thousands of validators in a substrate chain that is supported, right? You cannot even verify hundreds of them. Forget hundreds, even tens of ED2519 signatures are extremely computationally expensive to verify inside Ethereum. And that is one of the fundamental reasons why we have been constructing a ZK proof of it. A ZK proof that verifies all the thousands of signatures all in one shot. And not only that, there is this common prefix problem, which means that it is incredibly hard to take one block and show finality of it. You have to show that finality was happening because it belonged to a prefix of a particular fork, a fork which were attested by the supermajority of the validators, not that particular block. Now, what's the solution? Succinct had one of the fastest implementations of ED25519 verifiers inside ZK. And they also had a Blake2B verification that is possible today in production at a very efficient level. Now, Blake2B, as you guys know, are ones that is used as the hash function in substrate chains. And together, the ED25519 verifier and the Blake2B efficient hash function construction made it possible for us to create a ZK circuit which efficiently verifies Grandpa consensus. We actually took it a notch up. We saw that what's the best kind of verifier optimizations that we can do. We actually not only made the ZK verification around 200K gas in Ethereum, but also we had multiple batches of these blocks recursively verified together. So not only was there one ZK proof which verified that a particular block was actually final, it actually included a range of blocks all together verified inside the other ZK circuit. Not only that, we actually used it to parallelize it. Now think of it like you have 10 different blocks. You don't have to wait for sequential construction of proofs. You can parallelize them together, and then together you can have one recursive zero-knowledge proof which verifies in 200K gas that the entirety of the fork that you're talking about is actually attested through consensus of the other chain. Then we improved that. This was what was there in production a few months back, but then we saw that the maintenance of the Grandpa circuit is tough. Any one of you who have ever attempted to write a ZK circuit by hand know it's incredibly tough to maintain it because of the huge amount of knowledge you need to have to create those gates, to make it optimized, to audit it. And not only because we had audited circuits and such, but then also the confidence was not that high because not many people can actually read that code and verify it. So we implemented it in SP1. SP1 is a general purpose ZK VM which turns your Rust code into a ZK verifiable program. That is what meant that we could take a Rust code which verifies grandpa and then prove it inside a ZK verifier in any chain of your choice. And as I said before, we moved to Helios from telepathy on the Ethereum to Avail side. But let's talk a bit about how it works, right? So essentially, we had to modify the substrate header to make sure that you can actually attest to header fields. Because one thing that validators don't do is that they don't actually have any attestation over the block body. They have the attestation over the block header, which means that any information which you want to pass through to the other chain needs to be inside that block header. And that's why we created a field called data root, which is essentially a composed root of two things. One is the blob root and another is the bridge root. Not going into the details, essentially it looks like this, where any blob that was submitted as part of the DA publication is essentially a leaf of the blob root. And any message that was passed as the bridge is essentially part of the bridge root. These are ABI encoded for just ease of decoding. And then together we created the bridge palette and the API, which happened to verify the Merkle-Patricia proofs of Ethereum message inclusions inside our bridge palette. And it's pretty simple. Like if you think of the overall level, you have a send message function in the vector palette, which essentially waits for block inclusion on the Ethereum side, then fetches the proofs from the bridge API and call the receive token function. This function can be your wrapper contract, anything of your choice. You can build an arbitrary wrapper contract to pass messages which you want to have on the Ethereum side or any other smart contract-enabled platform. And then on the other side, it's pretty similar. There is a step function because Ethereum consensus and its gadget, it's a bit dissimilar with the grandpa gadget. Grandpa does it over common prefixes. Ethereum does it over multiple level of slots. That's the Casper 3, the modified Casper FFG protocol. And because of that, there is a bit more hooves that are going to be there, because we are now having to use the storage proofs and Merkle-Patricia proofs and so on and so forth, which gets a bit tricky when you want to implement it inside the bridge palette. But roughly speaking, it's pretty similar. You have a send avail contract on the Ethereum side. You wait for the slot to be on the avail. You check the slot to block mapping because blocks mean nothing. Everything is mapped to a slot, and slots are what get finalized. And then on top of that, you fetch the proof and then call the execute. I would love to, stop at this and happy to answer more and more questions on this. But if you want to quickly look at the ZK circuits, the proofs, this is the updated repo here. It is developed by Sussing Labs and Avail together. It's called SP1 Vector. Inside there, you will find another archived repo, which was the original Vector ZK circuit implementation, if you are interested in that. Otherwise, would happy for if you guys looked into the Rust code and checked if we are missing anything. Also on the Avail repo, there is the bridge palette, which which verifies this entire ZK construction. Thank you. Happy to answer more questions.
Awesome. Thank you, Prabal. And do we have any questions out here? I'll come and bring you a mic. Any questions for the speaker? No? Emil? No questions whatsoever? I'd be interested to know. Oh my God, hold on. What's your question?
Hi, Prabal. So my question is around, there is a new, as you might already aware, this Hyperbridge launched. So that's, I believe it's a pessimistic bridge where it verifies these signatures, but it's still cost efficient, I guess. So what's the overall, in Avail cases makes sense because you just want to verify the attestation, but what's the major advantage of the ZK bridge, because though the verification fees on the chain level is reduced, but still the proof generation cost of a substrate chain, I believe it will be very high, and that is being done at the SP1 or like your centralized system.
So there are two components to that, right? So one is what you mentioned as the centralization piece of it. The other is the cost optimization piece of it. And then the third, three pieces. Then the third is essentially the pessimistic or the security piece of it, right? So one thing, again, I want to start from the very beginning is like there are multiple types of bridges. The most that you can do ever at an information theoretic level is the trust minimized bridge, which verifies the consensus of the other chain. Now this comes to what the security is that whether you want yourself to verify it, whether you want a crypto economic set of validators to verify it, or do you want a smaller set to verify it, right? Now there are all these types of bridges, different types of different bridges, and there are fantastic kind of work done in the Polygon ecosystem and beyond about the types of bridges that are in production. What we are trying to achieve is the highest form of guarantee. We want yourself to verify it. You do not rely on any other crypto economic stake. No matter if you have $1 billion or if you have $1 million or if you have $1 at stake, it doesn't matter. It's a validity proof that you yourself can verify inside your wallet. That is the reason why we have been developing this ZK bridge. Next, coming to the cost. The cost of ZK proof production is non-negligible. Completely agreed. And that is why what we have done is we have done two kinds of optimizations. One is parallelization, where you can produce multiple proofs in parallel. Second, we made it in a way where you can use any of the proven networks. So there are now coming up proven networks which actually efficiently generate your proofs. Not only that, actually today in production, there are two proof aggregators who are actually aggregating Avail proofs. One is Nebra, and the other is, I'm forgetting the name. But these two, the Electron Labs guys. So both of them, what they do is, they not only take Avail's proof, they take multiple of these ZK proofs and then aggregate them together and verify, which makes the verification even cheaper, right? So these two optimizations makes it extremely easy for you to generate and verify proofs in a cost-efficient manner, and that is what we have been working with, right? And then the third is the centralization factor. Mind you that this is only a liveness failure. Even if the centralized entity completely gets corrupted, it can only halt generating proofs. And this is a trust minimized, which means that anyone has have that information. You yourself can fetch those proofs from the RPC and then generate this ZK proof, right? It's a Rust code at the end, which means that you can verify it yourself, again, coming back to the same point, but the corrupt entity cannot generate a false proof. That's the soundness guarantee of a zero-knowledge proof, right? So that's what makes this the most trust-minimized model that you can have. And that's why trust minimization is the point that I keep on saying again and again, because of course there are trade-offs there. If you want trust minimization, there comes the innate cost. The innate cost is of generating the ZK proof.
Thank you very much. Looks like we have another question right here.
Hey, Prabal. Yeah, I'm just curious if you, during design of Vector X, consider the case, for example, well, in substrate-based systems, sometimes we might have, for whatever reason, the case when finality stops. But as you said, liveness is guaranteed, so we still can produce blocks. But what we end up in this situation is that we produce so many blocks, and now at some point finality is live again. And now we have to prove, because the grandpa proof now could be very huge. As you see, we might have many forks, and grandpa justification is large. Did you consider that? And is it going to scale in case of that kind of failure? I think it's the same case could happen. Well, kind of similar thing can happen when you increase number of validators, for example, in Avail, because you can also have more forks. Grandpa finalizes not as fast because now we have this all-to-all communication stuff, which gets slower. And again, the proof is increasing. So yeah, I'm just curious. Did you run any kind of these tests for when grandpa proofs is really larger than usual?
Yeah. So I mean, Kamil being coming here, that he is asking exactly the Achilles heel of this construction, right? So what happens is, in a ZK circuit, no matter whether you do it using a Rust program or anything else, it gets cross-compiled to a RISC-V program and so on, but ZK proofs cannot have unbounded iterators, right? So every ZK circuit needs to be a finite depth, and you create a proof on that finite depth, which means that I cannot have a for loop which I do not know how long it will run. I have to put an upper bound. In our case, the upper bound is the era length, the era for which the validator set remains same. And after that, you have to force a validator set change. And after that, again, you can compose another proof. So there are two essential functions which we prove in zero knowledge. One is the finality, and the second is the validator change. For very large number of blocks, what you do is you force through finality. You do not use the grandpa gadget. In substrate, you force through finality, essentially saying that this set of validators do a special vote saying that forget grandpa for a moment, I actually go ahead and finalize this particular block, right? And everyone in before that is essentially validated and finalized. So similar constructions are here. That's the forcing function, and that is essentially why we are having to have a small committee which essentially can do it in emergency. So we have to pass a governance proposal, and if the governance proposal passes, only then you can force through that function on the bridge level. But because of the ZK limitations, you cannot have unbounded logic in it.
Thank you so much. Any other questions? Oh, I got one way back here. Hey, let's try this out. That was a bad throw. It's left the building. Okay, try it out.
Hello. I'm generally aware of the availability of many different precompiles across ZK VMs, including ED25519 or the curves that enable it. I was curious if what, if any, criteria was given to deciding on a ZK VM?
Essentially, the journey was not like that, if I have to be very, very honest. I think it can be done in any ZK VM, but succinct SP1, because we had been developing with succinct for a very large amount of time, this was even before they had produced SP1. We were working with succinct. So naturally, the precompiles of Blake 2B and ED25519 actually helped us ship it faster and implement it faster. But we also work with RISC-V for Nexus and other constructions that we have. And although they do not have the Blake 2B hash function, I do not think that implementing precompiles are always tricky. It's easier to hand-wave it for me and say like it can be done. But I am pretty confident that it can be done in any ZK VM, succinct being more optimal because of the journey that we have had with them.
Thank you very much. Any other questions? Okay. Probably lots of really smart questions here. I'm wondering, for any of the developers who are just starting out, maybe they're at home and they're inspired by what you said here on the stage today, what advice would you give them for getting started in Substrate?
So in Substrate, one of the major features is that you can start anywhere. Like, again, I am being a bit dishonest here when I say you can just hack on any piece of code. But essentially at the palette level is the easiest to go in, take a look at a palette, like break it. I started from the other deep end where I wanted to break the header structure first, which was a wrong choice in hindsight, but I learned a lot because of that. So palettes, I would say, are the first steps that you check, that you guys should check out in Substrate. If you're interested in only zero knowledge proofs and verifying that, check out the SP1 and the RISC-0 stack. You can take any Rust code and make it ZK verifiable.
That's great. It was awesome to have you here. Thank you very much. Round of applause for Prabal. Okay, we're going to take a wee half-hour break, and then we're going to return for an awesome talk.